Hi, Precalc. This is going to be day 0, and I know it's a little bit weird to title it that way, but the intro to our unit on trigonometry. Now, the title of today's lesson, which is the foundations of trigonometry, and that's really what this is all about. This, the video is really critical to get you a good understanding of things that we're going to use throughout the entire trigonometry unit, which lasts almost an entire quarter. So if you've never watched a video closely before, this is the one you really got to pay super close attention to. And I'm hoping it is somewhat of a review for you. So in the first definition at the top, we're defining what an angle measure of a radian is. So it says an angle measure of 1 radian occurs when the radius of the circle is equal to the measure of the intercepted arc. So here's a diagram to illustrate that concept, that this angle theta right here is going to be equal to 1 radian when the radius of the circle and the measure of the arc that's intercepted by this ray right here, when those are equal, this angle is defined as being 1 radian. And what happens is if you copy that over to get a 2nd radian right here, and then eventually a 3rd radian, you find that that 3rd radian is almost halfway around the circle. And it takes just a little bit more than 3 to get halfway around in terms of radians. And it turns out that 180 degrees is equivalent to pi radians. So if we had more time to do an investigative and exploratory activity with radians, we would do that. But this might be something that you've done in geometry or even in algebra 2. So there's definitely some common equivalents that I just want you to know how to convert back and forth between. And these are ones that really come up very commonly in terms of the number of degrees in each of these, and then how many radians would they have. So we know that 180 is pi, and if I kind of work backwards from there, this would be half of 180. So this is half of pi, or pi over 2. And if you compare all of these to 180, then you're going to be able to come up with those radian equivalents. If we know that 360 is double 180, then we would expect 360 to be 2 pi. So I'd fill these in pretty quickly in your table below. I'm hoping that, again, these are kind of common radian equivalents that we would just know if I said, hey, 60 degrees, you know it's pi over 3. If I say 30, you know it's pi over 6. These are ones I want you to be super familiar with and just be able to kind of tell me at a moment's notice. Okay. Well, if it's not one of those very common equivalents, how do we do the conversion process? Well, if you're converting from degrees to radians, you're going to take the number of degrees you have and multiply it by pi over 180. Because if you actually come back to this equation up at the top here that say that these two quantities are equal, if you divide both sides by 180, you have that every 1 degree is pi over 180 radians. So therefore, if I want to have the number of degrees I have here, multiplying that by pi over 180 converts to radians. Similarly, if you divide the pi to the other side, every 1 radian is 180 over pi degrees. So these are the two conversions we have to know. Here are 2 really quick examples that I'll illustrate the conversion for. So if you have 120 degrees, what you're going to do is you're going to multiply that by pi over 180. And then the last step is really to reduce that, because if I multiply by pi over 180, 120 over 180, well, certainly we can divide the 10 out right away to get 12 over 18. But beyond that, the top and bottom are both divisible by 6. So this is going to reduce in the end to become 2 pi over 3. So 120 degrees would convert to 2 pi over 3 radians. And notice how that's double what 60 is, which makes sense. If 120 is double 60, then we would expect when we do the conversion to get double pi over 3. Similarly, if I want to convert from radians to degrees, 3 pi over 4, I'm going to multiply by the reciprocal, 180 over pi, and what you'll find is that those pi's will cancel. 4 winds up going into 180 45 times. So multiply across the top, 3 times 45 is 135 degrees. To make a connection to something in the chart, it kind of makes sense that if I have 3 pi over 4s, that it's 3 times 45 degrees. So that's another quick way to get it. If you know pi over 4 is 45, just triple that, multiply it by 3. All right, moving on from there, we're going to talk about the basic trig functions. There are, in fact, 6 of them. And you learn 3 of them in geometry, and then you probably add the next 3 on in algebra 2. But I'm hoping maybe the pattern SO, CA, TOA will help us in evaluating within right triangles. So what I want you to do in the triangle below is label the sides in the following way. So we have the angle theta as this kind of base angle down here in this right triangle. And I've labeled the sides as x, y, and then r for the length of the hypotenuse. So let's talk about the three that we're probably most familiar with based on SOHCAHTOA. We're going to figure out what sine theta, cosine theta, and tan theta equal based on the values that are given in this picture. So sine is going to be opposite over hypotenuse. That's what SO stands for in SOHCAHTOA. The opposite to angle theta is what's across from it. So opposite is y. And the hypotenuse is the length of r. So sine theta in this picture is going to be y over r. Cosine theta is going to be ca adjacent over hypotenuse. So the adjacent's the x, the hypotenuse is r. Cosine therefore is x over r. By the way, if anything here is just very familiar to you, feel free to kind of fill in the rest and move on to the next page. Finally, opposite over adjacent. The opposite is y. The adjacent to angle theta, the side that's touching there, is x. So tan therefore is y over x. So these are three that I'm expecting you to be pretty familiar with. You've done them for a couple years now if we think about prior years of math. But the other three maybe we're not as comfortable with or just as familiar with, at least, because they're reciprocal functions. And the reciprocal functions have the names cosecant, secant, and then finally cotangent. And I'll tell you, cosecant's the reciprocal of sine. It's 1 over sine theta. And the easiest way to do this to figure out the ratio for cosecant in this picture is not to do 1 divided by y over r, but to simply flip that fraction over. It's just r over y. It's going to be hypotenuse over the opposite. Similarly for secant, secant's the reciprocal of cosine. So 1 over cos theta in this case would be the reciprocal of this ratio. So that would be r over x. And finally for cotangent, which is 1 over tan, that would be the flipped x over y. So hopefully that kind of looks familiar to you, these names. It takes a little while to remember that cosecant goes with sine and that secant goes with cosine. Tangent and cotangent are usually pretty easy to pair up with one another. Okay, moving on to the next page. On the next page, we have some information regarding what's called the unit circle and how we can evaluate within the unit circle. What we want to be able to start building here is evaluating sine, cos, and tan specifically. We could do the reciprocals too, for what are called the quadrantal angles. So if I ever refer to something as being a quadrantal angle, it's an angle that falls on the quadrant borderline. So in this unit circle, the point 1, 0, it's called the unit circle, by the way, because the radius is 1. And this point corresponds with 0 degrees. As I rotate counterclockwise, up here would be 90. 180 is on the left. Another 90 from there is 270. And then finally, 360, we've come full circle by the time I get back to where I started. Because we know the radius is 1, we can identify these points on the outside. And you also have to add into your diagram this triangle that I've created in the first quadrant. If I pick a random point somewhere on the outside of the circle, to get to that point, I have to go to the right x and up y. So you can see I've labeled those two sides of the triangle. Because it's a unit circle, we know that the radius is equal to 1. So based on all that, I want us to determine what is the ratio for sine of theta. Sine, remember, is opposite over hypotenuse. The opposite of theta is y, and the hypotenuse is 1. So whereas if you compare this to what we just wrote on the other page, I think we listed the hypotenuse as r, right? Now we're saying that this hypotenuse length, instead of y over r, in a unit circle, that length of the radius is 1. So sine theta just corresponds with y. And if you do a really similar process for cosine theta, cos would be adjacent over hypotenuse, x over 1, which is just x. And it brings us to a really important concept with unit circle trigonometry. Any point x comma y on the unit circle could be expressed as cosine theta sine theta. And we're going to use this really important relationship in just a moment to be able to determine sine and cosine of these degrees, 0 degrees, 90 degrees, and so on. Let's actually do that right now. If I said, what's cosine of 0 degrees? Well, 0 degrees corresponds with this location on the unit circle. Cosine of 0 goes with the x value of that location. So cosine of 0 is 1. I'm not sure how I started with cos, but let's go backwards to sine then. Sine of 0 would be the y value of this point on the unit circle, which is 0. So that's what I'm going to do for each one of these points. As I circle around the unit circle, sine goes with the y value, and cosine goes with the x value on the unit circle. Let's just work across the row for sine first. So as I go to 90, we can see sine of 90, if we look at the y value, is 1. Coming around to 180, sine of 180, y value is 0. At 270, the y value is -1. And by the way, these last two columns, 0 and 360, are in the same spot, so those should always be the same. Okay, so we get 0 for there. If we start back where we at the beginning and we look at the x values for cosine of 0 we said is 1, cos of 90 is 0. Come around to here, cos of 180 is -1. 270, we're at 0. And finally, back full circle, that's going to be a 1. Now, how do we get tan, though? Tan we haven't really addressed yet on the unit circle, so let's go back to our picture. What's tan theta equal to? Tan theta is going to equal opposite over adjacent. It's going to equal y over x. So for tangent on the unit circle, you could always do y divided by x. So, and if you look at your table here, oh, aren't all these the y values and these are all the x values? So tan is kind of interesting because it could be expressed as sine over cosine. And since we have the rows filled in for sine over cos, to get tan, which we said is y over x, you're going to divide top over the bottom. So 0 divided by 1 is 0 for tan of 0 degrees. Tan of 90, however, 1 divided by 0 is no good. It's undefined. Can't divide by 0. 0 over -1 is 0. Tan of 270, issue again with 0 on the bottom. That's undefined. And then tan of 360 is 0. We'll eventually use this information to generate what the graphs of sine, cosine, and tangent look like. So we'll get there eventually. All right, moving on to special right triangles. Again, this is jam-packed with information here. What I want you to do for the special right triangles is know that we have a 30, 60, 90 triangle on the left here. And then we have a 45, 45, 90 special triangle on the right. And you can see in how that the sides are always in a certain ratio for these triangles. In fact, you might remember these as having x's next to them. So maybe this is 1x, x radical 3, and 2x. Okay, so a 30, 60, 90 pattern would always fall into this ratio of sides. So for example, if x was 2, it would be 2, 2 radical 3, and 4. But for our purposes and what we're going to be doing, we're going to assume that x is 1. That's going to be the easiest thing for us to do, is assume that x is 1 and go with the values that are just listed in red there. So based on that, if you have those values filled in, and I know I'm going kind of quickly here, so feel free to pause along the way, we should be able to very quickly find the value, the exact value. I'm going to even throw that in. These are exact values with radicals of cos 30, sine 45, and so on. So I'm going to fill this in pretty fast. Remember, cosine is adjacent over hypotenuse. So from 30 degrees right here, the adjacent's radical 3, and the hypotenuse is 2. Make sure you're using the correct angle, because if I went from 60, that's going to be a different case. Sine 45, I'll tell you for 45, it doesn't matter which of those angles you use. You can use one or the other. If you use the one at the bottom, opposite over hypotenuse for sine would be 1 over radical 2. Now, you might be used to this, that we rarely leave radicals in the denominator. So if you multiply by radical 2 over radical 2, that's called rationalizing the denominator to get a final answer here of radical 2 over 2. Right? So no more radicals in the bottom. This is typically how you would see the answers accepted, as radical 2 over 2. Tan 60, tan members opposite over adjacent. The opposite is radical 3 from 60, right? Make sure you're going from 60. Opposite is radical 3. The adjacent side is 1. Radical 3 over 1 could just be written as radical 3. And if you feel like you kind of got the idea, try this bottom row. Hit pause and try those. But otherwise, I'm going to fill them in pretty quick. Tan 45, go to this triangle. Opposite over adjacent is 1 over 1, which is just 1. Sine 30, come back over here from 30 degrees. Opposite over hypotenuse would be 1/2. And finally, cosine of 60, make sure you're using 60 up here. Adjacent over hypotenuse would also be 1/2. So these are values that I would expect you to come up with pretty quickly, but you definitely have to memorize these two patterns. These are so critical for so much of what we do with trig. If you don't know these two special triangles, you are going to be so lost in this unit. Don't let me down. Got to memorize those two special triangles. I'm really hoping they look familiar from the past 2 years. Okay, last but not least, rules for evaluating. We're now going to kind of extend beyond just looking at 30, 45, and 60, which all happen to be in quadrant 1. We're going to be able to do something like the sine of 210. And we're going to sketch that angle first. We're going to create a right triangle with the x-axis. Find what's called the reference angle. The reference angle is an acute angle. and then label the sides and evaluate. So let me just jump right into it and show you what the process looks like. First of all, 210 degrees, I'm hoping you can picture that that's going to be somewhere in the third quadrant. And when you sketch an angle, you start from 0, which is on the right side of the x-axis, and you rotate around until you get to the quadrant that that angle ends in. I know it's in the third quadrant because I know that the borders there are 180 and 270. So go ahead and stop that angle at approximately where you think 210 would be. And like I said, you're going to construct a right triangle with the x-axis. Don't go across to y, come right back up to x. So it's really important that you do that. When you construct a triangle with the x-axis, all of your triangles should look like part of a bow tie. I should never see any bow ties connected to the y-axis. It's always going to be a triangle. Here's your quadrant 1 triangle, 2, 3, and then 4. What's the reference angle? The reference angle is this piece right here. Okay, so what's the acute angle that's just in that third quadrant? Remember that we've already taken up 180 halfway around. Well, I'm hoping that you can in your head say the full angle is 210. If I subtract 180, that's what I'm left with on the inside here. So this is 30 degrees. Oh wait, 30 sounds familiar. We know a special triangle where one of the angles is 30. We're going to use these side lengths, 30, 60, 90. Okay, so across from 30 is going to be a 1. Across from the 60, which is technically down here, is a radical 3. And the hypotenuse is 2. Before I fill in the ratio for sine of 210, I'm going to do two things. Okay, I'm going to label both of these as negatives. When you're at a point in quadrant 3, to get there, you went left and down, both of which are negative directions. So putting negatives on those legs are pretty important. I never label the hypotenuse with a negative, just kind of a general rule of thumb, but the legs, depending on which directions you're going in, may need negatives. Okay, sine of 210 is going to be equivalent to sine of this reference angle. So if I think of sine as opposite over hypotenuse, the opposite's the -1, and the hypotenuse is 2. And you can check that on your calculator, by the way. We'll do a little bit of calculator checking over the next few days. Sine 210 is -1/2, and we're done. Let's move on to cosine of 150. Cosine of 150, 150 is going to be in quadrant 2. Okay. If we think about quadrant 2, what I want you to think about is to find the reference angle, which again is this piece inside that right triangle. We've already gone 150. How much further do I have to go to complete the half circle? Or take a half circle and subtract out 150. That's going to be another 30 degrees again. So if the reference angle of 30, you're going to say across from that is 1, radical 3 is down here, and then 2 is on the hypotenuse. It's going to be a pattern that comes up over and over and over again. Do we need any negatives anywhere to get to a point in quadrant 2? How do I get there? I go left, that's negative. Then I go up, that stays positive. So the only negative that you need is on the adjacent side of radical 3. Now keep in mind, cosine's adjacent over hypotenuse. So the adjacent is negative radical 3, the hypotenuse is 2. Cos 150 is negative radical 3 over 2. Probably won't do the rest of these, but let's just do a few more just to kind of get the hang of what's going on here. Let's talk about if the angle is negative. So tan of -135. If you have a negative angle of rotation, that means that you're rotating in a clockwise direction. It doesn't mean the angle is physically negative. It just means that the way you rotate, instead of going counterclockwise like I usually do, you're going to go or clockwise, I should say. So -90 is right here, where 270 would be. -180 is halfway around still, which means -135 is going to be in quadrant 3. The quadrants do not get renamed just because we're going in a clockwise direction. So the negative just told me which way to rotate, but technically I've gone 135 in this direction. So the question becomes, well, how much is left over here inside the triangle? Well, if you think about this as half a circle, 180 minus the 135 leaves you with 45 degrees. Again, happens to be a special triangle. They all should be special triangles. If you're left with 20 degrees, it's no good. Got to go back and fix it. All right, so in a 45-45, the legs are both 1s, so it's 1, 1. And then we put radical 2 on the hypotenuse. That's the pattern for 45-45. The 1s are both going to be negatives, because in quadrant 3, we're going left and down. Tan, remember, is opposite over adjacent, so it's going to be -1 over -1. Opposite over adjacent, which turns out to +1. Okay. So notice how sometimes the answer will be negative depending on what quadrant I'm in, but I could be in quadrant 3 like I was earlier and get a positive result, specifically if I'm working with tangent. And we'll talk about some patterns that exist where certain trig functions are positive versus where they are negative. I think I'll finish up by doing maybe this row right here, because we got some radians and I like the last one in that row too. And then we'll of course get more practice in class next time I see you. If we have a radian like 5 pi over 3, I'm going to encourage you not to convert this to degrees. I think that's a quick, easy way out if you get stuck, right? Multiply by 180 over pi, figure out where it is in degrees. But without doing that, let's see if we can remember that this is pi and this is 2 pi, right? Because we know that if we go halfway around 180, that's what pi radians is, and then full circle is 2 pi. Well, if I convert this to something with the denominator of 3 to make my life a little bit easier, pi is the same thing as 3 pi over 3. And similarly over here, if I want to make the denominator 3, you have to multiply the top by 3. So I'm going to rewrite this as 6 pi over 3. And knowing that tells me that 5 pi over 3 is in quadrant 4. Because in between 3 and 6, by the way, this would look a little bit weird, but it would be 4.5 over 3 right down the middle at the quadrantal there. So 5 pi over 3 is definitely in this quadrant right here. Here's my question. How much further do I have to go to get to 6 pi over 3? If this angle on the outside is 5 pi over 3, this whole thing, don't I just need another pi over 3 to get here? And if you don't love pi over 3, remember if pi is 180, 180 over 3 is 60. So this reference angle of pi over 3 is the same thing as 60 degrees. However you best see that in your head, this way you can label the sides. Across from 60 is radical 3. If the 30 is down here, up here would be 1, and then we get 2 on the hypotenuse. All right, do we need negatives anywhere if I'm in quadrant 4? To get to this point, I went to the right. The right is a positive direction on the x-axis, but then I'm going down. So we do need a negative on the side that's labeled as radical 3. Sine, member, is opposite over hypotenuse. Opposite the reference angle is negative radical 3, and the hypotenuse is 2. You're going to see a lot of these same answers start to come up over and over and over again. Notice how that's the same answer as number 2. Okay. All right, let's talk about cos pi over 4. Pi over 4 as a radian angle actually does not leave the first quadrant. Because if you think about halfway around being pi, which would be 4 pi over 4, and here's 0, 2 pi over 4 is right in the middle. So 1 pi over 4 is just that angle of rotation right here in quadrant 1. Pi over 4, by the way, it's halfway in between the quadrant borderline, so it's an angle of 45 degrees. You don't have to convert that to necessarily know that. It's just a good equivalent to know that this is 45. That's the 1, 1 radical 2 triangle. If you're in quadrant 1, you don't need negatives, right? In quadrant 1, you're going to the right and you're going up, both of which are positive directions. Cosine's adjacent over hypotenuse, so that's 1 over radical 2. Like I showed you earlier, you might want to rationalize that answer. That's typically the accepted form. Finally, you get radical 2 over 2. Okay. Last thing I'm going to do, and then I said we'll do a lot more practice in class next time I see you. Sine of 270. Where is 270? What quadrant? Well, the answer to that is sort of a trick question because it's not in a quadrant, is it? 270 is right on that borderline right there. It's not in quadrant 3. It's not in quadrant 4. So if you find that you're working with an angle that's on the quadrant borderline, this quadrantal, I'm going to refer you back to the unit circle. Okay. So if I think about the unit circle whose radius is 1, this goes with the point 0, comma, negative 1. And remember, that's an x, y coordinate pair, right? This is the x value, this is the y value. So we just have to remember, what does sine go with? Does sine go with x or does sine go with y? Well, it turns out that maybe a quick and easy way to remember is that it does go alphabetically. X comes before y and c comes before s. What that means is that sine goes with the y value of that point. So since sine is equal to y at 270 degrees, the y value is negative 1. So therefore, sine 270 is negative 1. And we should be able to do then any quadrantal knowing that sine is y and cosine is x. We can do some others. Promise we're going to do more with this. I know that was a lot of information to throw your way on just day 0, not even day 1. But day 1 is a lot more practice with these same concepts. So let me know if you have any questions as we're working through day 1. Otherwise, have a great rest of your day.